few minutes. By that time, we can talk to each other. First of all, I am feeling happy to see you after a long time, your face. And Reena may be also feeling very well because you have worked together. Reena ji, your comments, please.
Yeah, yeah, I think it is so nice to see all of the familiar faces. I am seeing
Uh,
Rina after a while, and as well as yourself as well, because it's almost 2 years, right? It's a
More
two and
than
a
two
half years,
years. More
more
than
than two
2 years.
years that I
Uh,
met you in
uh,
Lucknow. Yeah, and so you are one person that a lot of people from Lucknow they cannot deny uh, their presence, whichever event, whatever event, and the different platforms where you call us and we get together. I think thanks to you, Dilipji. I think it is a great service and for bringing all of us together, irrespective of whether where they are in Lucknow or not. They're in Lucknow at this point of a time, right?
Actually, our original name is Association of Knowledge Workers Lucknow, but now we are removing the word Lucknow because internet has made it a global. Why we should say that we are only local? So we are local plus vocal both.
Right, right, right.
Uh,
Absolutely, absolutely.
Madam, Reena, you can unmute.
We are not able to hear you, Rina. So I think you will have to unmute.
Yeah, I'm so sorry. Can you hear me now?
Yes,
I had
yes, yes.
yeah, a different level of mute on my microphone actually. So I was just saying that hello Arvind. I said that probably you didn't hear, and then
अभी था
also
चालू ऊपर गया
wanted to mention that Mr.
यार
Dilip
इसको
Kumar
मत
had
लगाना
reached
इधर
out
आपके नहीं काम कर रहे हैं ये काम कर रहा है
in the same spirit that I'm originally from Lucknow, have spent a lot of my career years also in Lucknow in the past, and he
ये
reached
काम
out
कर रहा
and
है
told me to join a group that he has
यार
created
बड़ी मुश्किल से अभी आया
for all people from Lucknow who may now be at different places, right? So I think it's a great commendable effort to get people together, irrespective of where they are. Yeah.
Right, right.
Arvind ji, namaste. Manoj.
Manoj ji, yes, yes. आपका वो book and as well as the topic, the VUCA world, right? So whenever I hear that particular terms, I remember you, Manoj.
Thank you very much.
VUCA, I know that you have come out with a new release,
Yeah,
new.
this is the latest one. No, this is the latest one, and it has the impact of the post-COVID on the entrepreneurial ventures at time.
Oh, very
And
good.
there was an interesting video call yesterday with Department of Defense US. So they are trying
Mhm.
to work on some of the initiatives on mapping uncertainties and complexities in the this Central Asia, Central Europe perspective. A very sensitive meeting, and I was happy that they have now engaged me in a project in trying to understand the Plutonomics actually. So wonderful to be
Very
doing
nice.
some work in that direction. You lost
Very
some
nice.
weight, sir.
Yes, yes. So, and in this COVID time, I thought that there should be something different. Okay. So, I
How?
uh, enrolled myself in the Ministry of Ayush Yoga Certifications Board protocol instructor course. Okay. So, this was 3 months, 4 months long courses, and I religiously followed all the recommendations, both from asanas to pranayams to the food habits and etc. So,
So
I'm feeling happy.
this is good to hear. I think we have met Reena ji. I have met and I've heard her also. Very excitingly, I had scheduled that today. I'm going to hear her about her on quantums. And at any point of later date in your institution, if there are some knowledge sharing series, I would like to share some outcomes of the latest book, which talks about the entrepreneurial initiatives and in terms of the startups and the complexities they've undergone. So once, if you have a 45-minute schedule or half an hour, 1 hour, then probably over Zoom or something, we can do that as well for you.
No, I
Sure,
will do
sure.
that, and even Rina and as well as myself, Manoj, and I will also request Rina as well. So there are so many. there are different platforms, right? So IEEE RINA is also member of IEEE. So a lot of such webinars and knowledge sharing session happens. It is important, I think, for all of us, as we claim ourselves as a bit experienced people, that to share those experience and knowledge, right, amongst the new generation and industry. That's important. Yeah.
You are
Yeah.
based at
So
Nagpur.
now I think it is 3:05, and so should we start as the people join, or should we wait for a couple of more minutes?
We have 43, sir. Dilip ji, we have 43. I reminded people on the group. So they have 43. You can start, sir, on time if you're on time.
Okay.
State Saab bhi aa gaye. Professor State Saab is also there now. Very
Hey,
much.
hello.
Yeah. Namaskar, Shetji.
Namaskar, namaskar.
Hello.
Hi.
Yeah. So let's start. I think we have the right quorum, and we should start uh, for the benefit of all the people, all the participants who have joined this particular webinar. It's very important and very upcoming new, right? So thank you, Dilip ji. And at the outset, I would like to thank Dilip ji to organize this webinar. KWL, LMA, and the other platforms all coming together for this knowledge sharing session, and also an opportunity given to me to introduce my colleague Rina, right? So we have been together in our professional journey for so many years, right? So, and we have seen each other growing, learning, contributing to the cause of technology and the IT industry. And right from the days when enterprise storage as a terminology was not so known in India, grasping those opportunities and creating center of excellence, building team around those concepts and skills, providing thought leadership as part of the organization, and as well as SNIA, Storage Networking Industry Association, and then embracing further as technology evolved, the cloud computing, and getting into the CCICI, right? So if I pronounced rightly, Cloud Computing Innovation Council of India, then active member of IEEE, then founding chairperson of IEEE Special Interest Group on uh, Quantum Computing India, and all of these immense contributions from Rina on the technology
हाँ, वो
leadership in
तुम्हारा
India,
मैं
right?
नाम दिलीप वहाँ दिखा रहा है, या उसको बंद करके री रजिस्टर
And
करो
Indian IT industry.
अपने
Dilipji, you
अपने
can mute yourself and show that, yeah.
ओके.
So she is also a certified corporate director and member institute of directors, uh, patent holders, author of book Innovation Magic: The Science and Art of Innovation Management, then Chevening Fellow of the Rolls-Royce, alumni of Tata Group Executive Leadership Program, and then Roche School of Business, and so many things, so many things, and to talk about it, and after her successful stint in TCS and Microsoft, now she is currently the CEO of Benzitin Advisors, in fact. Okay, and so beautiful journey, and quite enriching journey, I would say that, and both on the professional front and even otherwise. I am sure that all of us, the participants, and will have a virtual but immersive learning experience on quantum, right? It is a new word, new terminologies. Not too many of us know about it. So even the definition of it is also is going to be quite enriching, right? So, but yes, we are going to have beyond that, and how does this uh, upcoming technology impact on society, as Rina takes us through its evolution, the tech areas, the impact on the industry, the society, and what does the future look like, right? So there's so much to learn, and I'm personally excited to listen, and I'm personally excited to learn from Rina, and I'm sure that all of you as well. Okay, so I would not like to speak much on the topic because I'm still ignorant, and I would like to learn from Rina. Over to you, Rina.
Thank you so much. I'll also go ahead and share the screen. Just to give a little bit of context, thank you so much for that wonderful introduction, Arvind. And I think I'm remembering the time when I was in TCS in Lucknow, and the fact that the teams were working on such a rare, very cutting edge area called storage networking at that point in time, where nowhere in India people were working on it. And in fact, people wonder even now that, how come, I was staying in Lucknow and doing such amazing work, right? And, because it was amazing at that point in time to be working in that space. And it was very, very enriching, in fact, I could say that the foundation for working in emerging tech areas was laid there for me, because I continued my journey on working on cutting edge technology. So while Benziton Advisors is focused on emerging tech areas, what I also did, and this is where quantum comes in a little bit more, is that I established a not-for-profit entity called the Quantum Ecosystems and Technology Council of India. The mission of this entity is to actually enable and accelerate the quantum ecosystem in India. So we want to be, I felt that there was a gap in India for a private entity or an institution which could support all the efforts that the government, industry, academia is doing in that space, and which can bring all the stakeholders together so that this complex area can move forward a little faster. There was also a need to reach out internationally and see how international collaborations could fill the gaps that are there in India. Now, it seems like a tall order. And in fact, to be very frank, last year when I left Microsoft, and this idea had been germinating in my mind because I was involved in the ecosystem, and I wanted to do something like this. And then there was this tiny little voice which was telling me that, that's a very tall order. Who do you think you are? How will you do that? Right? So there's this always that voice which says, maybe this is too big. But then, I just, that voice became little meeker, and the other voice which said, no, but this is needed right now, and it is very important, became stronger. So ultimately, I spoke to a few people. I found people were very, very supportive of what I was trying to do. And so we set up this company, Section 8 company last year. And in fact, we kicked this QETCI off with a quantum symposium, national level quantum symposium, which was a 6 days long symposium where we invited anybody and everybody who was doing anything in quantum in India, both from the government, industry, academia perspective. And very interestingly, I wanted to also gauge, how much support are we going to get? And I'm sharing the story for a reason. Let me just complete it for 2 more minutes. What we did was we wanted some people from the Department of Science and Technology, or because there is a space angle to it also, ISRO, etc., to be part of it. And I was not sure. I felt that I have not really, in the last few years, I was more focused inwardly on products and a little bit on the ecosystem. My engagement with various entities in the government was very limited. So we nevertheless sent out invites to the ISRO chairman, the Department of Science and Technology, MITI secretary, and principal scientific advisors office, thinking that even if one of them agrees to come to the symposium, then we will sort of be able to take the discussion forward and feel more motivated. To her surprise, each one of them accepted the invite. And last year, when we kicked off the symposium, during the symposium, we launched QETCI. And we had the principal scientific advisor, the chairman of ISRO at that time, MITI secretary, DST representation, local state IT department representation, everybody there. So what that message, the message that I got at that point in time, along with other folks who were passionate about this, is that, you know, there's a desire in every part of the ecosystem to engage and make this happen in India, because this technology is going to be transformative in a format like never before. We are sort of standing at the cusp of a computational revolution very similar to the one which happened when for the first time computing was discovered, and, you know, we had the first set of classical computers. And very interesting thing to note about computational progress is that it's not taken us hundreds of years to actually progress in a very exponential manner. If you look at the history of computing, we have actually made remarkable exponential progress in a matter of decades. We may not realize it, but if you consciously look at the history, it's not about centuries, it's about decades in terms of how progress has happened. And, you know, adaptability of human beings, the society, the environment, and the businesses to this new form of living, which comes with the new form of technology. I'm still talking about classical computing, has been so remarkable. It speaks about the agility of the human society. It speaks to the agility of the humans themselves. And then also how quickly businesses adapt to all of this. Now, we are at a stage today where every single business and industry today can be called a technology industry, right? Because there is a very strong role that technology plays in any industry you talk about. In that context, I wanted to go, you know, and talk a little bit about uh, the quantum area itself, right? And what I'll do is, because this is a debate, I will take some time to talk about what is quantum in as simple a language as possible. But if things do start getting complex in your mind, please remember that this is a complex topic by nature. So it's okay if it is a little complex, as long as you understand the gist of how this computing is going to revolutionize the industry. I think it's fine. So this is what the history of computing looks like, right? And literally, the first, just to give you a sense of, you know, how things have moved. You know, in some senses, even an abacus, which was discovered long ago, is a computing device because it allowed you through a device to actually do faster calculations. And of course, 1822, when Charles Babbage discovered the difference machine, I think that was the first time we had the inkling of what we know as a classical computer today will look like. In that sense, that's the reason why Charles Babbage is also called the father of modern computing. And from 1822 till now, we are talking about a couple of centuries, and look at the amount of progress that we have made in these times. Now, if you look at the history of how computing has evolved, our entire computing is driven by the semiconductor technology evolution. So technology has followed Moore's law, which means transistors have continued to shrink. More density of transistors in semiconductor chips, which have enabled miniaturization of devices over a period of time. And now the semiconductor industry has reached a stage where the CMOS technology, experimentally, there is availability of knowledge, I would say, because commercial availability is still a little down the line. Last year, I think TSMC demonstrated 1 nanometer capability, right? So I think that's gone really small in terms of miniaturization of the technology. As technology has miniaturized, more computational power has become available to us. That is how computationally we have grown from a certain stage to where we are today. Now, when we go in the semiconductor technology to levels below 1 nanometer, those quantum effects start to come into play. And I'll talk a little bit about that in a minute. And therefore, the question that is there in the industry and has been there for some time, and we may not witness it if we are in a different industry, or if we are not directly working on a semiconductor side, we may not realize that Moore's law is coming to an end in some senses, because that technology has reached its limit. And now the question that everybody has been asking for some time is, what is the next opportunity for evolution in the technology space? And therefore, in the last several decades, scientists and researchers across the world have been working on several different computing approaches to identify what is the next generation technological computing technology going to be. So this includes neuromorphic computing, which is understanding how the human brain works and mimicking the human brain to see how computational entities could be created. Molecular electronics and chemical computing, where some kind of a chemical or molecular reactions are being used to represent states for computing, and the reaction itself would represent some sort of a transformation, right? So what do you need for computing? You need a reference like a bit, 0 or 1, and then you need a transformation on the bit, which is what we do in classical computing. You manipulate these bits through different algorithms to create something else. Now, if on the underlying physical layer, instead of semiconductor, you replace it with something else where you can represent something as a unit of information like a bit, and some other transformations which could actually, on which algorithms could be built, then you have a new dimension of computing, right? So I think, so neuromorphic computing, chemical computing has been explored. Quantum computing has been explored for quite some time. And today this seems to be the most promising area. A lot of money and investment coming in across the world from various governments and private entities in this space. So we do believe collectively as an industry that this is the next opportunity from a computing perspective. Then DNA-based computing, fair amount of research has gone in that space. What has been discovered is that, you know, there's an interesting opportunity there for long-term storage, but maybe not so much from a compute perspective. Then, of course, some very fancy exotic experiments happening on the artificial organic brain or wetware computing, where there is an attempt to look at biological cells, experiment with them along with silicon to, you know, sort of create this hybrid computing mechanism, right? And while this may not result in a full-fledged scalable computing mechanism, it is yielding some very other interesting insights which may be applicable for biomedical areas, or, you know, some other problems that could be solved using this. So this is where quantum computing comes into the picture in the larger scheme of things from a computing perspective, and the reason why there's so much investment that is happening in this space. Now, when we talk about quantum effects, you know, I know that there are people in this group who may not be really physics people, right? But just to give you a little bit of sense of what's happening in the on the physics side, I mean, I'm sure all of you know Einstein and have heard his name. And you know people from that era where there's a lot of scientific research that ended up happening. Since then, since Einstein's time, I think till today, there has been a fair amount of progress in terms of physics. So what is the fundamental question that physics is trying to solve? Physics is trying to solve how the fundamental question of how and why the universe works and exists, right? How does the universe work? So what we see in our day-to-day life on a generic level has been explained to a large extent by classical physics, like Newton's law of motion. And, you know, so if you apply force to something, it will, you know, there will be, and the force is large enough to get the body to move, there will be an acceleration. So force is equal to mass into acceleration. So just an example. So all of physics is trying to explain how the world around us works. The place where physics actually fails to integrate is at two places. One is at very minute levels inside the atom. When you come to below nanometer distances, there is something called quantum effects that comes into play. So there is a whole branch of physics called quantum physics, which explains how things work at that smaller scale. The second is that most of these classical equations that explain everything around the world, they also fail when you look at very large contexts, like a lot of phenomena in the universe today are not very clearly explained, like dark energy, dark matter, and you might hear about these in popular science journals and so on. Also, in terms of what happens at the edge of a black hole. So, of course, the holy grail of physics is to try and integrate all of these behaviors to talk about one fundamental principle on how the universe operates. Now, thankfully, because of this attempt by the physicists, there has been a lot of research on the quantum physics side. And what happens at the quantum physics side is that very strange behavior happens with the particles. These particles, which exist at the quantum levels, exist as particles as well as waves. And there is, I won't go into the physics of it, but if I want to explain to anybody, what I would say is that it is impossible at that level for anybody to pinpoint the state of a particle at any point in time. And when you do measurements, those microscopic measurements of those particle states, what happens is that it appears that until you measure them, they are in all possible states at the same time. Okay. And let me explain that by this example. Let's say we think of an entity like an electron. So for those people who do not understand what an electron is, if you're not from a physics background, if all matter, if you think of anything, it is made of atoms, and inside the atom, there are particles. Let's assume electron is a particle, and you can think of it as a ball which is rotating at a very, and let's say I want to identify that when this is rotating in the clockwise direction, I give it a value of 1, like a bit value. And then when it is rotating in this direction, right? Now, this entity, it exists in such a manner that in any possible direction. It can rotate in any possible direction, right? Now, but I want to identify only these 2 directions, and these are the 2 directions that I get when I measure, right? Now, the state where the electron is actually could be in any rotating in any possible direction is called a superposition state. And the reason why it's called a superposition state is because it's as if the electron is on all possible states of rotation until you measure it. And the reason I'm sharing this with you is because of this capacity of very strange behavior at the quantum level, we get a remarkable computational advantage. And the advantage is that what ends up happening is that you are able to now, if there are infinite number of a very large number of states that the electron can exist in at the same time, each of these states is used for calculation, and you get massive parallelism. And please forgive me, anybody who is scientific here will understand that I'm doing a little bit of a stretch when I'm using the word parallelism. But in order to explain this in a simple manner, it's almost, if I want to do a search in quantum, I would, actually, and there is a database of a million elements from which I have to search and match something. In quantum, I can essentially give the instruction to match against each element, and that is a single step operation because of these superposition states. As opposed to classical computing, where you will have to go and search against each element. In some algorithm, you'll use some algorithm to speed it up, but it will still be a massive search. It will take a finite amount of time. Whereas in quantum, it will come back. The search will come back in a single step operation. And that is exponential progress in computational speed. So this is one characteristic at a quantum physics level, which gives us exponential advantage. There is another characteristic, and this is something which, if you find it very weird, please be happy that Einstein found it weird as well. And he called it spooky action at a distance. And what it means is that at the quantum level, when somehow 2 particles get entangled together, which means that they share a coherence of properties or an entanglement or correlation of properties. And I'm being very unscientific again, but let's say that their properties somehow get correlated. Now, if you separate these particles and you can take them far apart, as far apart as possible without delinking them, maintaining the relationship. Then if the other particle is theoretically at the other end of the universe also, and if you make a change of state in one of the particles, it is automatically reflected in the other particle as well. Now, this is what Einstein calls spooky action at a distance. And this is non-local. All of the physics that we know is about what happens in a system, in an environment, and how all the parameters in that system change. And now we're talking about something which is not impacted by anything around it, but at some random distance, some other particle with which it has a correlation, something happens, and there is an immediate impact here. Now, this seems to be violating a lot of physics principles, but it has been found to be true. It has experimentally been proven to be true. Okay, so this is another feature called entanglement, which comes in very useful for quantum communication and computing also, especially in the area of quantum security. Because, without, in this case, if you have two entangled entities at different distances, and one of them is tampered with, you can get to know at the other end. So at a very high level, that gives certain properties become available to us for quantum security, right? So that's the reason why this technology is promising very exponential capability. For people who are a little bit more interested in the physics, there is some information here. I can share the PPT later, but I'm not going to go through that. So now we're talking about a quantum computer which provides us with performance gains in the billion-fold realm and beyond. And I will explain how that happens. I've explained a little bit, but I'll explain a little bit more. Now we are realizing that if you have a fully scalable quantum computer, which we don't have one today, we have a very good quantum computers with 100 qubits and 157 qubits and all, but what we need eventually is, let's say, a 1,000,000 qubit quantum computer. And what is a qubit? Just like you have a bit in as a measure of information in a classical computing, you have something called a qubit. It's a whole new information theory and whole new abstraction of computing. Right? So we are looking at a completely new way of designing systems. So we have qubits, and qubits can represent a very large amount of information because of this quality of superposition. Just to give you a context. Now, if you have, let's say, in a classical computer, in today's computing, if you have 1,000 bits, in 1,000 bits, you can store 2 to the power 1,000 numbers or values. Right? Now, if you look at, because of superposition, if you look at qubits, for 1,000 qubits, you can store, you're talking about 1.07 into 10 to the power 301 information units that you can store. And just to give you a sense of what this number is, if you want to count all the stars in the known universe, that number is of the order of 10 to the power 250 or less, or 287 or something like that. And we're talking about a number just in 1,000 qubits, which is way beyond that number. So the moment you go to 1,000,000 qubits, we are now talking about computational capacity, which is actually billionfold. More than that, we're talking about computational capacity that has never existed. Today, for example, if you look at the biggest challenges that the world faces in terms of solving problems, we do not know how the human brain works. Why? Because in order to model the human brain neurons, even the largest supercomputers, you're able to, sort of model just a very small fraction of the brain surface. We don't have enough computation. So what happens when you have a computation of this kind available? Can we model the entire human brain and understand how the human brain works? It seems very, very likely. So suddenly we are seeing possibilities of solving these problems in a very different manner. Today, if you look at astronomy, we collect a lot of data from the stars, from the universe around us. Do you know that all of this data is not completely processed till today? There's a lot of data which needs to be, people keep going back to that data, looking at it, processing it again because of limitations of computation. So in the future, you could literally be collecting all this massive amount of data from these different stars around the universe, and you could be actually processing them in some sort of real time or near real time, and getting the kind of information that you've never got before, which means you can suddenly discover other planets which could be habitable. And these are very difficult problems at the edge of our capacity, and that's why I'm mentioning them. I've heard this argument where people say, why should we bother about what's happening in the rest of the universe, right? Let's take care of Earth first. But just that these problems are not even solvable to that extent today, and they're going to become solvable. If you want to look back on Earth and look at humanity, today drug discovery takes a certain amount of process, because the whole process of searching for the right molecule in the drug takes a fair amount of time and energy. Now imagine if you could simulate that, if you had enough computing to simulate that and run the simulation, the kind of simulations they show in science fiction movies, where somebody in the future is doing a drug discovery in near real time, right? Actually, that might become a reality because of the computational capability that becomes available to us. And in fact, today, there are more than 15 well-funded startups around the world who are working on drug discovery using quantum. And this is also important because quantum chemistry is one of those areas which is emerged as a very strong subfield of quantum. Since even with simulations that are available today and the capacity that is available in quantum computers that exist today, it is possible to simulate a lot of these molecules and chemical reactions using quantum chemistry concepts. What is quantum chemistry? Applying quantum concepts to the chemistry environment, coming up with the right kind of algorithms that support that, creating the right kind of APIs that people can use. So I think that progress has been a lot more than many other areas, right? So I think there's a huge opportunity there, not just for drug discovery, but for material science and several other areas, which get impacted by chemistry. Now, when we talk about quantum, very often you will, think of only quantum computing, right? You'll say, okay, yeah, we're talking about a scalable quantum computer. But the reality is that there are many streams. There is quantum communications. And in fact, this is a well-known fact in the quantum space, but people who are working in this space, but in India, India has made a lot of progress in quantum communications. There are projects that have been going on with ISRO and Raman Research Institute, where they have demonstrated free, quantum communication using photons in free space. And then they're working on a scenario where you could do secure quantum communication via satellites, right? And then these are the kind of projects and that are happening across the world. We also have a startup in India, which is leading in this space. They have been able to create quantum networks using the secure quantum networks using a technology called quantum key distribution, using optical networks, right? So connected lines. And over a period of time, the amount of distance that can be covered is gradually increasing as they're making more progress. The same is true for a lot of companies around the world. A lot of countries around the world are creating these prototype networks, which are based on quantum technology. There are quantum annealers or specific hardware. So just like on the currently, if you look at classical computing, you will have a lot of smaller devices, smaller circuits, which do very special things. And these are smaller ICs, integrated circuits, which are application specific and so on. Similarly, on the quantum side, there are annealers and specific hardware, which are tuned to actually do very specific problem solving, right? Then there is also this area of quantum sensors. In fact, quantum sensors have been around for some time. It's just that people have not really paid attention. They have not captured the imagination of the general public. But there is a lot of progress happening in this space. Just recently, there was, very interesting sensor, which was developed, which allows the capacity to actually see what's happening to 1 meter under the ground. So very useful for infrastructure projects, very useful for any mining operations, very useful for identifying seismic activity to a much finer grade and predicting earthquakes and so on. If you look at the Charles Webb telescope that has been recently deployed, the capacity to be able to these sensors that they use, which are super cooled on the Charles Webb telescope, they are quantum sensors. So I think some of the meteorological sensors can be much better. Atomic clocks use quantum sensors, right? They're based on cold atom technology, which is a specific type of technology, but very, very so great opportunities on the sensor side as this area develops. So much on the manufacturing side, supply chains, mainstream businesses will also start benefiting from it. So this is, and a lot of progress happening in all of these areas across the world. In terms of scalable quantum computers, where are we? There's been rapid amount of progress in the last few years. And the last is, I think 127 qubit IBM announced in November 2021. Recently, I heard about a 200 plus compute capability from somebody else. And many of these entities are actually promising up to 1,000 qubit computers in the next couple of years, right? So, and remember that number that I told you, 10 to the power 301 with 1,000 computers. The challenge right now is twofold. One is number of qubits and the other is the noise in the circuit at that space. So creating more reliable qubits for computation, but this field is progressing very rapidly. So just to understand where are we across the world, there are huge government programs running across the world, whether it's Canada, China, India, some federated programs across multiple countries, for example, UK, USA, Japan, Canada, Italy, Belgium, and Austria, working on a connected quantum network through a company called ARKit. And then so like a private player has come in and they're helping them, these countries create a connected network. And of course, a lot of test beds in USA, Europe, China, India, and Japan, and several research projects happening in the quantum communication side. Hardware, a lot of hardware companies across the world. The interesting thing right now in the quantum space is that the hardware approaches that different companies have taken are very, very different. So somebody is using photonics, somebody is using superconducting qubits. This is all technical jargon, but what it means is that what is interesting to notice that some of these technologies are based on approaches which require cryogenics or supercooling, right? Close to 0 degree Kelvin kind of temperatures. If you see a picture, if you search for quantum computers on Google or Bing, what you will see is a picture, which shows a huge refrigeration unit, and the chip is slightly smaller in the center, right? Very, very small in comparison. So those are the traditional approaches which are based on cooling the environment around the chip to very low temperatures so that the noise is almost eliminated. And there's an opportunity for very sensitive qubits to be formed and manipulated. But there are other approaches that have emerged in the last few years, which include things like NV diamond, which is faults within diamonds where lasers are used to manipulate states of the ions inside that space. And that is used in either sensor technology, and it also has some promise for quantum computing itself. Similarly, photonics-based solutions. Photonics is based on photons. Photons is nothing but light. So laser or light-based technology, which is also at room temperatures, and then some very exotic solutions like topological qubit, which Microsoft is working on. Topological qubits actually take that physics is another level of it talks about two-dimensional particles, right? Particles which exist only in 2 dimensions, and then they emerge in our three-dimensional world in certain formats. So I don't want to go into the details, but there's some very, very fancy physics and very, very revolutionary work happening in some of those areas as well. software, a lot of companies have decided to start creating the multiple layers of abstraction on these hardware so that people can start programming using quantum, and these are the various interfaces that are available today. All of these companies have made these development environments available almost freely and open sourced it. So if there are people who want to learn how to code in quantum, you can just go search for these online. There are a lot of tutorials that are available and things like that. And QETCI itself, we've been conducting awareness sessions for programmers specifically, and larger awareness sessions with engineering students. We partnered up with the government of Telangana, and we actually did awareness sessions across all the engineering colleges in the state, and we want to do those kind of activities with different states so that students can become aware of what this area is. And if they, somebody who's, let's say, studying engineering right now or studying physics, doing BSc, and then at least they get to know what is it like to have a career in quantum, what is the opportunity for them to do higher studies. And people have lots of questions like that, and we want to be able to bring that to the students so that more people can consider this area as well. I think we're towards the end of the time, so I'm going to talk about two things and have a little bit more discussion around how society is likely to change. Before I do that, I'm going to look at the questions. I've seen a lot of comments here. Yes, some Anuj Mehrotra has written, if we compare electron with coin flip scenarios, superposition can be considered as a scenario where coin has both states at the same time, heads and tails. That's very good explanation. That's very perfect. Thank you for mentioning that. Then one form of probabilistic reasoning. From Manoj Joshi. Yes, absolutely. I was not sure whether we should use the term, but yes, quantum computing is all, quantum physics is all about the probability of finding, if you talk about an electron, finding the electron in a particular state. If you talk about a photon, then the probability of finding a certain polarization of the photon, right? And angle of polarization, degree of polarization. QC is one of the computing paradigms using concepts of quantum mechanics, superposition, and entanglement interference. Yes. Then a comment on QNU Labs. QNU Labs has been working with Indian Army for implementing secure communication. That's correct. In fact, absolutely. And I'm regularly in touch with the team in QNU Labs, the CEO, Mr. Sunil himself. And then, yes, they are a pioneering company, and they're doing remarkable work in the quantum security space in India. Now, coming to this question of what are the kind of problems that you can solve with quantum, actually, there's no industry where there isn't a problem that you can't solve in using quantum. The only thing I would like to mention to people is that it's not as if today you can take quantum computers and replace classical computers. And it's not as if that is going to happen in the next 5 years also. And I'll tell you, quantum computation is based on probabilistic scenarios. Now, if you wanted to add a series of integers, you can use classical computing. Why would you use quantum computing? Because quantum computing will give you an approximation based on a probability of finding that actual sum of those integers. And you don't read a probabilistic answer for something which you can solve very easily in a very certain manner, right? So there's a lot. So the future that I see is a hybrid scenario, which is what is emerging today as well, is where you write a program which makes certain calls to a classical computer, makes certain calls to a quantum computer, and they continue to exist side by side. And that's how computation is going to work until we make some really major breakthroughs in quantum and realize that we don't need classical computers, but we are not there. And I think just for everybody's sake, quantum computers will not replace classical computers. quantum computers will add to classical computers, and together these two computation technologies will continue to exist for a fair amount of time in the foreseeable future. So that's how I see it. And a good example of how you can understand nature better by using quantum is this example, which I give very often because I just really like this scenario. If you look at how nature uh, creates fertilizers, right? How does fertilization, how do organic material get broken in nature to create very useful elements for in the soil? It happens with very little energy consumption. There are certain bacteria which do nitrogen fixing bacteria actually do their job, and there is no harmful effect to the environment through these processes, which nature does. But when we do fertilizer production synthetically, we use something called as a Haber-Bosch process, which only has a 61% efficiency, which means that if whatever energy you put into this process, 40% of it is lost. It doesn't create anything useful. And the process is done very unnaturally. It is done at 450 degrees centigrade and 200 atmospheric pressure. So, that's where all the effort and the energy is going in. And the reason is because we do not really understand how the nitrogenous molecule actually interacts and acts as a catalyst. That's because with classical computing, it requires 10 to the power 32 bits for representing this molecule, and then more for actually analyzing any reactions with more molecules around it, right? So this becomes a very difficult, non-solvable problem with classical computing. With quantum computing, you just require 108 qubits to simulate the nitrogenous molecule. And with those 108 qubits, you can simulate it, and actually, which means that capacity is available today to actually figure out the most optimum way of doing fertilizer production. So look at the use case, which is already existing, and there are companies and researchers who are working on solving this problem and have made a fair amount of progress. So for all those people who say, hey, quantum is tomorrow's technology, I want to bring attention to things like this, which is, where problems are getting solved today. Even when we look at quantum sensors, a lot of these sensors are being used today. So this is no longer tomorrow's technology. This is no longer talking about the future. It is talking about what is happening today, how you can leverage today, and of course, how will it evolve in the future? So there will be evolution, there will be new stuff, there will be more growth in capacity in the future. And what is the only question that is unanswered at this point in time is which of these technologies at the hardware level is going to be the real breakthrough. But maybe more than one will be the breakthrough. Maybe we will have photonics-based computers as well as silicon-based computers, like say superconducting qubits at the same time. But that, you have to wait and watch and bet on it. India today has several startups working at the hardware software level, and the number is gradually increasing as we move forward. As QETCI, we are actually doing series of roundtables with international entities, Indian entities, large players, small players, investors, government entities to actually create recommendations for what needs to be done to speed up some of these processes. So I'll take a pause here. I think we're at 4 p.m. So any questions?
Hi, Reena ma'am. This is Anurag here.
Hi, Anurag.
Hi. I'm not an expert in the quantum computing field, but during this process of exploring quantum with you, I had one question. Can you put some highlight on the impact, on the security that will bring in when this quantum is coming up, right? We used to talk about algorithms, right? SHA algorithm. Quantum computer is going to break them in like few seconds or few minutes, right? Rather than years or something. So what will be the impact of quantum when you were saying, right, that ones and zeros will also coexist and quantum will also coexist, how would we handle the customer privacy and security challenges down the line?
That's an excellent question. And, it's a very important question. So let me answer it very briefly. What happens in quantum computing is that today, if you look at the security domain and look at the algorithms that we consider as non-breakable for now, is RSA 2048 bit, right? So
Right.
most of the world's data is today secured with RSA 2048 or AES-based encryption, which is hash algorithms. Now, each of these algorithms today it has been proven that they will be broken very easily by a quantum computer, right? Because what seems unbreakable. So the question that the world is facing right now is what happens post quantum. As soon as we have, let's say, 1,000-qubit computer, or even slightly bigger computer, let's say tens of thousands of qubits, what happens to what is considered as secure information today? So what happens to national security? What happens to the banking domain? Because, we know that even in cybersecurity today also there are rogue elements that exist out there, rogue nations that exist out there, which are supporting a lot of cyber attacks and so on. And our systems live online, right? So in that context, this becomes an extremely critical area. There are advantages on the communication side to use technologies like QKD, quantum key deployment, to create very secure networks. But what do you do with the data? Now, so there is something called post-quantum cryptography. These algorithms are being standardized. NIST in the US is trying to standardize these algorithms. There are discussions, not just discussions, there's a lot of work, open source versions of these algorithms existing. My message to the younger folks and people who are from the quantum security on the cybersecurity side is, hey, get together, work with these algorithms, form a company. This is where you will get the money in the future. And plus, India can have more companies working in this space indigenously, so that we can, because the transformations that will be required will be massive. To move everybody's infrastructure to quantum secure infrastructure. So there's a huge opportunity there, but it is also a big problem to be solved, right? So I think it's a very, very interesting area. It's a very critical and important area. There is a very big present danger also. So today storage is so cheap that, if somebody has access to the data streams of a company, of very critical data, it could be anything, either government data or it could be financial data. So what if you just to keep storing that data, 2 petabytes to whatever amount of, spend some money, some rogue elements could be storing that data today. As soon as a quantum computer becomes available, they can actually decrypt that data. So that's a big danger which nation states are considering right now. So there's a lot of focus on post-quantum security that is coming in. And India definitely needs more people, more smart people working in this space. So my message in every discourse that I do, every time I talk about quantum security, is that please get together, see if there are people who want to set up something in this space. There's a huge economic opportunity, but then more critically, there is a very, very strong need to actually have more people working in this space.
Okay.
Thank
you. Yeah, thank you.
Yeah. Reena, can I have a point to make?
Sure.
This is Prahlad Seth.
Yes,
and particularly coming to the drug discovery part, we have come a long way. We started with the the recent one has been the bioinformatics. And using the bioinformatics, people predicted these molecules, which could be perhaps the lead molecules. Then they said these could be the lead targets and in the drug discovery. Then now with the quantum computing, there's a basic question will be availability of the data sets, which could be utilized for computing. Now, I have this question in my mind that what is the accuracy? Because when we do with the bioinformatics, those molecules, when you take it to the lab, they really don't work that way. So when you predict something in the drug discovery, okay, this is the molecule which could be a personalized medicine, or this could be for many people or for certain ethnic group. As we are learning, the genetic makeup of the person also makes it different response to the drug. So I would like that you can throw some light on that aspect.
Sure. Sure. Very valid question. And I think the difference in the computational approach for quantum is that because you have this branch called quantum chemistry, which allows molecular simulation, that is one. What it allows you to do is to, the approach here is not going to, so one is it can improve the predictions first, because you can do a lot more computational correlation, and you can do a very different kind of machine learning, like quantum machine learning, to get better predictions. That is one. But more importantly, we are talking about simulation of molecules here. So which means you can actually do simulative reactions using quantum computational capabilities, which you could not do with classical computing. So instead of spending that extra effort in the lab, you actually zero down on the molecules to the next level. That's the intent, to be able to do that in the computational environment itself before you take something to a lab. So not only do you reduce the cost, but hopefully as the capacity of quantum computers increases, you can almost get near final identification of molecules in the simulation environment itself. Now, the second is genetic, dealing with genetic data is a huge cost, right? You need a lot of high performance computing as well as a huge amount of computational capability. And then also there's an overhead. You can't really do so much with genetic data as you would like to do. For example, theoretically, if you could simulate what kind of reaction different kinds of gene profiles are likely to have to a certain molecule, then that would take us forward, still generations. But so the promise of quantum, and here I'm talking about the promise because we still don't have a 1,000-qubit quantum computer. But I'm saying the promise of quantum here is to be able to help in that space as well. So it's just about a very large amount of computational capacity that is going to be available. And we have proven that molecular simulation is much more simpler and easier, and solutions have been derived in that space in quantum today. So when we put all of this together, we see certain things happening in the near term and certain other advantages coming in the longer term to solve this problem of drug discovery and its applicability, even to the clinical trial stage. If you could do something like genetic simulation before you take it out for trials in a particular geography with certain genetic quirks, if we call that, then that is also some of the areas which could be targeted in the future.
Thank you. Ed, one more related question. The government of India is giving a big push to Ayush medicines, which is as you know, Ayush, all Ayurveda, homeopathy, Unani. Now, these are all traditional material which has been used for a long time. Now, how this quantum computing can help in giving this push or bringing them to more useful so that people can get use of it?
So I think there's an opportunity here to use scientific corroboration of the effects of these medicines. If you believe that these medicines are useful, I'm one of the believers. I've spent all my childhood and a large portion of my adult life only taking homeopathic medicine, and I don't know if somebody can prove that scientifically that is creating impact the way rest of the medicines are proven scientifically. I think that will help a long way in going in this direction. And because you can simulate in quantum, you can simulate molecules, see the interactions, use better sensors to actually. I'm not really a medical professional, but I can sort of extrapolate that you can do more simulations and you can do more probing of what is actually happening when a medicine like a homeopathic medicine, which is diluted to such a fine level is, administered, and what is the kind of changes it causes in the human body. I think if we can now start looking at how to scientifically prove that, then suddenly, we could, I think, do a lot of good to this world. Same is true for Ayurvedic medicine, right? I mean, so at a chemical level, what are the kind of changes that it is actually causing? I think that's an interesting area of research, in my opinion.
I'm Anish Chansari. I wish to raise one or two questions. The anchor may like to. May I put up my questions? One is, in what way is the quantum computing going to enlarge the area of medical knowledge, especially in diagnostics and brain surgery? And second question is, I understand that human brain is still regarded as better place in terms of speed and solving the complex issues compared to the quantum machines. So is there any way to improve the efficiency of human brains with some kind of machine intervention so that the computing capacity of human brains is maximized? Two questions.
So, so the first question, I got lost in the second question. Could you repeat the first question, please?
It's about the impact which quantum computing is going to have in the area of diagnostics, medical diagnostics,
sure.
and discoveries of medicine, especially in neuro area.
Right. So already, I mean, there is there is proof of impact in magnetic resonance imaging, right? So when MRI scans are done, there is a whole lot of scans. It takes a fair amount of time to do the scans. And then when the images come back, it requires very specialized people to be able to look at the scans and decipher if, let's say a tumor is there somewhere, right? And so using quantum technology, and the reason why this is, not inaccurate, but it is not perfectly accurate, and why it takes so much time is because the intensity of the, there are certain things, and I'm not an expert in this space, but what I understand is that there are certain angles at which the MRI needs to be taken, and the intensity of the so there's some background noise. Anyway, so I think using the quantum based algorithms, it has been possible to optimize some of these things in a manner where it has reduced the time that it takes to do an MRI of a single person by, let's say, 20 to 30%, which means more MRIs can be done. And then when you look at those images, being able to predict that this is actually a tumor, and there is, early on, let's say in the case of cancer, can actually be very life saving. Now the other thing is, given that we have quantum sensors, one area which people are exploring and which I think there's an opportunity is that today we look at medical devices in a certain manner. We look at medical devices and we invent medical devices even from a diagnostic perspective based on current technology. What if, so when people think about quantum, you should not think about it just as, how can we make the current medical devices better? Physicists and people who are device experts on the medical side, can they work together, look at the new concept of quantum physics, quantum sensors, and devise new kind of devices, which are not only more efficient, but they work on fundamentally different principles than the devices that exist today? Because that opens up a very different opportunity. Again, this is a very, very specialized space. So, maybe you can say I'm just extrapolating here. But this is a conversation that we've actually had with people who are working in this space. In fact, somebody tried to push me to get into and start a startup in this space. And, I'm not a medical expert or a medical devices expert. So, and my colleague was something else. I'm more interested in actually enabling the ecosystem. But it's a very, very interesting area for now to see how quantum is likely to impact. Definitely, the sensors hold a lot of possibility. We've seen that there is an opportunity to make MRI scans better. Maybe new kind of scanning devices could be created for doing a check for the entire human body rather than getting into those bulky machines. Maybe some small devices could be created which are based on quantum sensors and are more efficient and more accurate.
My second question related to, is there any way which can be found out through quantum computing system to increase the efficiency of human brains, the computing capacity of human brains and the storage capacity of human brains, because it is given that human brain has much better performance efficiency than the present level of quantum computing systems.
You mean the current classical computing systems? Yeah. Yes, of course.
No, not classical. Even the quantum computing system is far behind the average brain computing capacities which human beings are endowed with. So the question is whether human brain itself can be increased, whether its efficiency can be increased by intervention of quantum computing. Interface between machine and human brain.
So I am personally not an expert in that space, but there are people who are working on it. For example, there is a company called Neuralink in the US, which is funded by Elon Musk, which is trying to figure out how to put devices inside the human brain. Their initial attempt is to solve the problem for neurodegenerative diseases like Alzheimer's or dementia. And also for people who are, for example, let's say crippled, cannot use a certain, after meet with an accident, cannot move a certain part of the body because the brain, the connection from the brain to the nerve endings of the particular limb are lost or something like that. So I think they're working on certain technology there. So there are companies who are, and there is research going on in that space, and there is actually a company which is trying to build an interface like that. I'm sure.
May I ask another question, last one? Does the time allow you to entertain?
You may ask.
I read somewhere that time travel is possible through the quantum computing. If you have very high grades of qubit capacity, then time travel in the past and in the future is possible. Do you think that this is correct and it's likely to happen in a generation or so?
That is science fiction, actually. As of today, if I'm a science person, then the only statement I can say truthfully is that is science fiction. There's a lot of stuff in quantum physics and some calculations that happen with string theory for explaining the universe, which yield very weird kind of scenarios, which means that when you do certain calculations, you get negative value of time in certain cases. And you know what the popular media does is they run away with those calculations and they say things like scientists go back 2 seconds in time, right? But that's not true. I don't think anybody has, at least to my knowledge, I don't think we've ever seen any time travel. And chances are if there was time travel in the future, we would meet some of the time travelers in our current timeline as well, right? So I'm pretty, I don't know what to, I think it's an interesting...
not to be quoted and taken very seriously. Muslim world believes that the Prophet Muhammad traveled in a very short span of time to 7 heavens and met the God and came back. And there is an empirical evidence that one or two of his companions, they testified that they saw that the Prophet disappeared from his bed, and when he came back, the bed was warm still, and the lock of the door was still moving around. So there is an empirical evidence. So from there, I have taken the jump, whether it is possible scientifically. Like they say that black holes can facilitate the speed and people can move very fast to intergalactical journeys. But is quantum computing...
So I'll tell you why it is difficult to answer that question. Let's take all of that in context. let's keep those, that evidence I cannot say anything about. But if I talk about it purely from a science perspective, today we do not even have the capacity. We have landed people only on the moon till now. Okay. And now there are discussions happening, plans being made for landing in the world to land people from Earth on Mars. And even that is a multi year journey back and forth. And today, there is, in the next 10 years, we are not going to have the capacity to go beyond the solar system because human lifespan is so less, right? So, and we do not have really concrete theories, even which are proven, which connect what happens at the edge of a black hole. And everything at the quantum level is not explained. We do not even know fundamental particles. We predicted that a certain number of fundamental particles that we discovered, there were more. Then as string theory is evolving, we're discovering, oh, there are the theoretical particles, right? So physics is not at a stage right now where it can concretely predict every aspect of human understanding of the universe, and it cannot therefore predict what kind of technology that is going to come in the future. If you ask me the question, is it impossible for time travel to happen? I will probably say, probably no. The probability that it could happen is a small number. It may be infinitely small, but it is still, there is a probability that is possible, right? So as long as that is there, the answer can be maybe it can happen in the future, because we still,
thank you very much. Thank you.
Yeah. All right. Thank you very much. I do have to jump into another.
Doctor, I request Dr. P.K. Seth to just summarize it so that we may close the program.
Rina, can you stop sharing your screen?
Yes.
Oh, so that we can see all people who are there. Okay, I think, Dilipji, you have given me a very difficult task. First of all, I'm not an expert of the physics, so who could understand all the basics. But yet, I must say that Reena ji has done a great job. And she's from the Quantum Ecosystem Technology and Council of India. And in a very simple manner, she has explained how the history was there, how it developed, and then what stage we are as the size got smaller and smaller, and the ability of the people to do things have increased. As far as the application of the quantum computing is enormous. It can be used in almost any field, whether it is the industry or it is the academia, or whether it is the medical technology. And very simply, everyday in use is it's used in the weather forecasting. Number of the factors are there which are computed, and then they predict that this is the weather which is likely to happen. Even in today's newspaper, it is said it is improving. It is improving because of these more and more technology. And as they become usable and people understand them, I think accuracy will also increase. In the medical field, imaging analysis is very important. You take a lot of CTs, you take a lot of echoes from the heart and the MRIs. But what is the baseline? For each patient, is it different? Or could there be thousands of these analyses could give you, okay, this is the baseline. Microsoft had done an exercise with the heart images, and Devi Shetty had said that what we thought of the normal heart echo is not really normal. It varies. So this is giving an advantage for prediction, and prediction in the more manner in which it is acceptable and more predictable. So we have come a long way. We were doing mathematical modeling, and I remember with my experience with the Industrial Toxicology Research Center that what will be the flow of the various contaminants in the Ganga River. And now if we had that quantum computing at that time, it would have been much more easier, but it was a difficult task to do it. We were taking a lot of time. So she explained that how it can be used in the medical sciences, and very encouraging point she mentioned that there are a lot of startups in India itself. There are 50 startups which are working in the simply in the area of the drug discovery. So imagine that what opportunity is going to give people for carrying out the work and predictive manner in which it will benefit the society in a very long way. Not only giving jobs, but also providing better healthcare and improving the infrastructure requirements which are needed. Because based on this, one can calculate or predict this is what you actually need. And I do not know how far whether it was used in the COVID case or not when we are trying to compute that about the what will be the number. I think IIT had done that job, and which is says the next wave will become in that time, and the third wave will second wave and third wave, and a lot of predictions were correct. So I think more and more as the quantum computing is done in our country, there will be more and more benefit. There's a long way to go, but at the same time, what is heartening is this, that we have people like Rina who have done this job, who have created this council, and I'm sure this will give people. She also said there's a lot how people can learn about the computing. She mentioned about the tutorials are there. So many things are there, and for all our young people for utilizing this could be it was also mentioned by Mr. Narota that QNU labs are working with Indian Army. So you see, there are a number of people, number of avenues, number of applications are there. I think coming back and very interesting point which Dr. Ansari added was about the brain computing and capability of the brain to compute. I think I will agree with him. The ability of the brain computing is enormous. And how the brain stores the data, it doesn't, and recall only when it is needed. It's not there, it's think of somebody, immediately his face comes up and all activities around him comes up at that time. Otherwise, the brain is silent, never worry about it. So it is on the lighter vein, yes. The travel time, I do not know whether it reduced or not, but we can travel with the brain. Somebody sitting in US, and if you think of it, his house, his garden, and everything comes to your mind, and you can see. So this mind traveling with the mind is really, again, I think how that is how the brain fixes. Rina also gave an example that nitrogen fixation. She explained very well how people can utilize in reducing the level of the fertilizer which is to be used. This will be very helpful. On one hand, economics, and the second hand, not polluting the environment or the soil with excess of the nitrogen. So I think I would like to conclude that the sky is the limit and human brain use is there. And yes, it could be useful for human brain, as she explained, when you have certain neurodegenerative disorders. You get people with a stroke, very recently it has been shown, people with a stroke, they are not able to convey. But in their brain, electrical signals are going on and they're thinking. If you ask a person, how are you? He can communicate with the eyes and one can feel he's saying all right. But now it has been possible to convert these his waves into signals, and those signals can be picked up and the answer can be written on the computer, I am well. So that is the, I think, is taking us to the limits that which are very, in the medical technology, there's going to be a lot of experience. I think Dilip ji and LMA has done a very good job, and I think brought in people to understand this upcoming quantum computing, and which will have enormous application. And again, I think human mind has to find more and more application. Thank you, Dilip ji, for giving me
I
this
want
opportunity.
I want to tell the participants that Reena ji's parents live in Lucknow, and sometimes she visits Lucknow. So I have taken a promise with her that in her next visit, she will give us 3 or 4 days where I will take her to certain engineering colleges and other places just to enlighten the people more and more in Lucknow. Okay, with this.
Doctors,
I have a
Shreyas,
request. I have a request. I have somebody waiting on another call for me from 4 o'clock
Okay,
onwards.
okay,
And
okay.
I realize, it's a very interesting, engaging discussion. And I'm very grateful for this opportunity. But to do so,
Okay.
I would really like to leave right now. Arvind,
Okay. Thank you, madam. Thank you very much.
डॉक्टर प्रहलाद आपको एक शेर सुनाना चाहता हूँ किसी बड़े उस्ताद साहब।
मैडम को जाना दीजिए साहब, पर हम
हाँ नहीं
लोग
मैडम
सुनते
चले
रहेंगे।
जाएं, मैं इनको सुना रहा हूँ।
हाँ।
अभी ये कह रहे
Thank
थे
you
कि
very
माइंड
much.
ब्रेन कैसे काम करता है।
हाँ।
एक उस्ताद शायर ने कहा कि दिल के आईने में है तस्वीर यार, महबूबा की तस्वीर जो है दिल के मिरर में, दिल के आईने में है तस्वीर यार, जब जरा गर्दन झुकाई देख ली। तो ब्रेन जो है उसकी कैपेसिटी जो एग्जिस्टिंग इस वक्त क्वांटम कैपेसिटी की जो मशीनें हैं उसके मुकाबले में सेवरल थाउजेंड क्यूबाइट्स ज्यादा है, क्यूबिट्स ज्यादा है। लेकिन उस ब्रेन की कैपेसिटी को हम लोग एनलार्ज नहीं कर रहे हैं। गवर्नमेंट भी और सोसाइटी भी ब्रेन के बहुत थोड़े हिस्से को यूज कर रही है और बहुत जगहों पर गलत जगह पे भी यूज कर रही है। तो वी हैव टू क्रिएट ए कंसेंसस कि ब्रेन का इस्तेमाल सही जगह पर हो ताकि लोगों का इलाज हो सके, ताकि रोजगार क्रिएट हो सके। ये नहीं कि सर फुटबॉल में जो है लोग अपना हो जाए। Thank you very much.
Thanks Arvind Kumar ji and many other important persons who have attended, and we will meet again. We will meet again. Okay, thanks. Good evening. So let us close it. Leave.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you.
Guys, what